Hey everyone, today we are going to talk about a special type of slope stability analysis called rapid drawdown analysis. And so when we have a dam or a levee, we analyze a number of different scenarios in terms of potential slope failure when we're doing the design. And a couple of the things we would analyze is we would do a seepage analysis with the pool in a full state, and that would give us a phreatic surface coming across here, and we can analyze slope failure on the downstream side, potential slope failure on the upstream side. But in many cases, the scenario that gives us a lower factor of safety is what we call rapid drawdown, and that's where this water on the upstream side goes from its normal pool to a lowered pool over a relatively short period of time that does not allow the pore water pressures to drain and equilibrate. So the problem is you end up with this upstream side is still saturated and therefore very heavy, but you lose the buoyancy effect of the water that was on there before. Therefore, the driving forces become very high, and it is what we consider for poorly draining soils. It would be an undrained circumstances. So you have undrained strains and heavy soils. That leads to a combination that gives you a very low factor of safety, and it's something you need to consider in the design. So when we look at this, what is considered rapid? Over what period of time would we consider that rapid? So Mike Duncan in 1992 suggested that we use the dimensionless time factor. Now, if you recall from consolidation theory, this time factor is part of the process of analyzing consolidation in soils. It's the compression of a soil under an applied load. And there's this dimensionless time factor, and it's the product of the coefficient of consolidation multiplied by the time elapsed and then divided by the drainage distance squared. The coefficient of consolidation is a function of how permeable the soil is, and when you do this calculation, if the time factor is greater than 3, then drainage should be sufficient. Therefore, it's not a rapid drawdown case. If it's less than 3, then we would go ahead and assume that would qualify as a rapid drawdown condition, and we would need to investigate it more thoroughly. Here are some standard coefficients of consolidation. Again, they're a function of both the compressibility of the soil and the hydraulic conductivity, and so they vary by many orders of magnitude. Sands have a very high coefficient of consolidation, but silts, compacted clays, soft clays, now it gets much smaller. So there's, again, a very wide range here. Okay, so here's some examples. So this is a dam. This dash line up top would be the pool when it's in its full state. And so let's assume, for the sake of argument, that it has time to come to an equilibrium in this state. We have a compacted clay dam or levee. It eventually goes to a lower pool, and if you pick a point somewhere here in the middle, our maximum drainage distance is 35 feet. So the drainage distance is for any point in sight here, what's the farthest it would have to go in order to drain, and anything down here would be straight up, and so this is probably the somewhere around here would be the farthest. And so if we plug in that drainage distance in the denominator here and square it, put in a time of t equals 50 days and a coefficient of consolidation of 2, we get a time factor of 0.08, which is far less than 3. Therefore, this would definitely count as rapid drawdown. So notice that 50 days might seem like a long time. Almost 2 months. That's still rapid enough that the soil would not have time to drain, and so it would be saturated, and it would be shearing under undrained conditions, and therefore we would need to analyze it as a rapid drawdown case. Here's another example. In this case, we have 3 materials. We have a core, a compacted clay core with the same 2 feet squared per day coefficient of consolidation, and then there's a fine sand shell. There's also some kind of filter here, but that's not given. But so let's for the shell, we're going to assume the maximum drainage distance is 31 feet. Here in the core, the maximum drainage distance is 14 feet. In both cases, it takes 50 days for the pool to lower. And so if you plug in the drainage distances, the time, the coefficients of consolidation, notice the sand has a coefficient of consolidation of two orders of magnitude greater than this, 200 feet squared per day. Oops. And if you plug that in for the shell, you get a dimensionless time factor of 10.4, which is greater than 3, so you would not consider that rapid drawdown. It would have time to drain and equilibrate. But the core, once again, it's 0.5, less than 3, so that would be a rapid drawdown case. So you would need to analyze this for rapid drawdown. All right. So what if a dam is newly constructed and it's filled rapidly, and then within a relatively short period of time, the pool is lowered, but right after construction, right at the end of construction, the soil has not had time to fully consolidate to long-term conditions, so you still have the stresses due to compaction and construction. If you have freely draining soils, again, use effective stresses and pore pressures from post-drawdown conditions, and you should be fine. Poorly draining soils, then you would use strengths from unconsolidated, undrained tests and just do a normal slope stability analysis. So this is a little bit easier than the normal case. So for long-term conditions, so assuming that the soil has been the dam or levee has been constructed for a long time, and then we have a full pool for a relatively long period, and then it drains under rapid drawdown conditions, as indicated by the dimensionless time factor. If you have freely draining soils, just use effective stresses and pore pressures and do a normal slope stability calculation. But for poorly draining soils, it is an undrained condition with the heavy soils. However, the undrained strengths that you would use in the analysis, it's a little bit trickier to figure out what undrained strengths you should use, and so the strengths you use will depend on the consolidation stresses prior to drawdown. And that is kind of the key point of a multi-stage analysis that we use for rapid drawdown. And so that's kind of the basic framework of the rapid drawdown.